Recording in progress.
Good morning, everyone. Well, welcome
morning.
to a new semester. Hi.
Morning.
Well, looks like some new people here. People I haven't seen before, I think. Although I do see a lot of people every semester. I guess we could start out by asking, how was your winter break?
I'm trying to think of the right word for it. Enjoyable.
Good?
I just really didn't feel like Christmas was all what Christmas is supposed to be this year.
Oh, like, what happened?
I just felt like I wasn't in it this year. I don't know. I think it came too quickly.
I know what my one word is.
Yeah?
COVID.
COVID.
Yeah, my whole family got it.
Oh, man. That's terrible. I hope they're doing okay.
Oh yeah, everyone's better now. I mean, if you're vaccinated and boosted, then it's just like a little minor cold.
Yeah. I was actually the guinea pig for my family and got the vaccine first. And then I told them to get it. And then sure enough, 2 weeks later, they all got it.
The vaccine or the
For COVID.
Oh,
But it does work.
Yeah.
I took care of all three of them, and I never got sick once.
well, my let's see. So I think it was my teenage daughter who brought it home, and so she was like coughing and had a fever for a couple of days, and then we all thought, well, we're all vaccinated, we're not going to get it. But then me and my wife started feeling like the sore throat and the runny nose. And we went, oh no, now we've got it. And then, like, what day was it? Like Christmas Eve, my 8-year-old goes, I have a sore throat. Like, great. You just got your vaccine like 2 weeks ago.
Right.
You know, and then my teenage son, he managed to somehow avoid it. Not avoid it, but not catch it, right? He just was fine
Right.
for like a month. And we said, well, you should probably go and get your booster. So we got his booster, and the next day, boom. I think what happened was his body had just been fighting it off the whole time. And then when he got the booster, the immune system went, I recognize that. And they just went into overdrive, and he was sick for about a week.
Oh.
So yeah, for about 3 weeks, we were all sick at one various time or another. But none of us got it, really super seriously. I guess except for my wife, who is, I think, still feeling some of the effects of it. She's just really tired all the time. So that was my winter break, COVID. So basically from the week before Christmas until all the way through New Year's, just everyone was sick. But got that over with. Now we're good. Well, the CDC says we're good for 90 days now, and then we can catch it all over again. How about the rest of you? Let's see. We've got a few more people here on now. We got 8 or 9 people. That's good. Well, of course, I should introduce myself. My name is Professor Barry Brown. I've been teaching here at Sierra College for 20 years now. In fact, I just got a little award for my 20 years of service to the district. So that's pretty cool. And hopefully we'll be another 20 years. Well, I don't know if it'll be that long. I mean, I'm already in my 50s, so I don't think it'll be that long. But this is Discrete Structures for Computer Science 26. We'll be streaming every Monday and Wednesday at 9:30 till 11 o'clock. And then on Wednesdays, we also have what would normally be our lab session if we were actually in the classroom. So I'm trying to keep that schedule because that lab session does give us the time to go over the assignments and to get your questions answered. Now, as far as doing the lectures here, I do like them to be interactive, so I haven't had a problem with people just speaking up anytime they've got a question. If it gets to be a problem, then we might have to, invoke some kind of, rules for engaging. But with only about 10 or 15 people here, you should just be able to speak up anytime you want. I don't require cameras to be on, but it would be nice once in a while to see your faces. So maybe if you do have a question to ask, you can turn your camera on. There will be some times when I might have you work out a problem on a piece of paper, and then you would just hold it up, to the camera and show me the results you have, or take a picture of it and upload it to the chat. So that's as far as the Zoom etiquette goes. Hopefully you can all make it here at the 9:30 time. I know for some of you you've got other things going on. It was particularly a problem last semester when a lot of people had morning classes actually on campus, and so they couldn't attend the 9:30 session. Just watch the recording later. It's really up to me, however, to remember to post it by the end of the day. Once I get off of Zoom here, then I've got a couple of hours to do work, and then I have to go pick up the kids. So it's kind of every day is drop off the kids, come and do this class, get some work done, get some shopping done, and then go pick up the kids. And so it's a daily cycle. And so sometimes I don't always remember to post the recordings by that evening. If that happens, then just shoot me a note or something. Says, hey, where's the recordings? And then I'll remember that night to post them. We are also being joined by some people on YouTube. Last semester, I decided on a whim kind of to just stream the class to YouTube and see what would happen. And so we've got people joining us from other countries. Maybe if the people on YouTube could actually just quickly say, like, approximately where are they from, like what country they're from or what part of the world they're from, and then we can find out where all of you are. And so what might happen is, for those of you who are on Zoom, the people on YouTube can hear you if you ask a question, but they can't see you. So even if you turn your camera on, they won't be able to see you. All they can do is see me. I was going to say something, and then I totally forgot what it was. It'll come to me in a moment. So the people on YouTube. Oh, another reason for doing the YouTube was last semester I had a student who could occasionally watch the live stream on Zoom, and then it was fine. Now the problem was he lives out in the foothills somewhere, so he doesn't have really fast internet access. And he wrote to me one night and he said, I wanted to watch your recording, but the Zoom recordings that get posted are really big. I mean, it's about 1 gigabyte per hour of recording, and so the recordings can be, up to 2 or 3 gigabytes for, the full 3-hour session that we do. And he said, because of my internet speed, it took all night to download that video, and I wasn't able to watch it till the next day. And of course that, wreaks havoc also on his data plan. So he said, is there any option for me? And I said, well, I could try streaming the class to YouTube, and then what would happen is if you watch it on YouTube, YouTube will of course adapt the quality and adapt the data rate for your particular situation, so you could watch it at a lower quality and it would not consume as much of your data. And he said that would be perfect, and so that's why I started doing this. And it was really fun also to see all the people who are on YouTube who are watching this. So we got some people from Serbia, Turkey, and Vietnam. So welcome to the stream. Any questions before we begin? Just remember, if you do speak up, even if you have your camera on, the YouTube people can't see you. And there may be some occasions when you might say something or ask a question that is private to the class. And if that happens, I've got a button on my control panel I can hit, and that will mute the YouTube stream. It'll turn off the cameras, and it will turn off the audio, so the people watching who are not in this class won't be able to hear or see anything that happens if something private is happening. And something private could be you're asking a question about your grade, or you're saying something that might be something that we would expect only people in a classroom would hear. Okay, so if that ever happens, I just punch a button and that mutes the YouTube stream, and then I can bring them back live when the question is over. So before the semester started, I sent out an email to everyone, and I included in that email a sheet of paper, a PDF that had a bunch of diagrams on it. And those diagrams looked like this. And the question was, which of these 6 drawings can you trace completely without lifting up your pencil and without overwriting a line? So you start at some point in the drawing, and you completely trace the drawing, and you probably end up where you started, and you have traced the drawing without over-tracing a line and without picking up your pencil. And the question was, which of these could you do? So maybe take a moment, if you haven't looked at them, take a moment to do them, and then put in the chat or speak up which of them you think you can draw. And by draw, means draw without retracing a line, and draw without picking up your pencil.
So I've got 2, 3, 4, and 6, but I couldn't do 1 and 5.
2, 3, 4, and 6. So your claim is, whoops, yes for this one. Didn't mean it to be so thick. Let me change that. Yes for this one. Yes. And would you say 4 and 6?
Yep.
Okay. And it was a no for number 1 and a no for number 5. And then Grace says you could do 2, 3, 4, and 6 as well. So 1 and 5 were both no's. I guess my next question would be, how long did it take you to figure this out? I mean, like 6 and 5 are pretty complicated. Was it like, had you spent like, I don't know, many minutes on those later ones, 5 and 6, or were you able to pretty quickly determine whether they could be done?
If you find out like kind of the pattern, it doesn't take that long. Like I was comparing 1 and 2 and what they had like in common, and what made 1 impossible and what made 2 possible, what made 3 possible as well. And then after that, like 6 kind of just came by, and then 5 I already kind of knew it won't work.
How'd you know? No, first of all, there's 2 ways to do these problems, and in fact, there's 2 questions to ask about these problems. The first question is, can they be done? Yes, no. And the second question would be a follow-on to the first one. If the answer is yes, then actually, how would you do it? And for many of you, when you try to solve these puzzles, the 2 questions get conflated together. That in order to figure out if the answer is yes or no, you're also along the way going to figure out how to do it, because you're sitting there trying to trace the drawings. But what I claim is that there's a way to separate those questions. There's a way to answer the yes-no question without knowing how it's done. And is that what you did? Did you figure out whether it was possible or not possible before you figured out how to do it?
I believe so.
Oh, so you might have found like something about the drawings themselves that tells you whether or not it can be done.
Yeah.
Yeah, and that's what we're going to explore over the next couple of minutes is there something about the drawings that we can just look at them and go, oh, I know what that one can be done, or I know that one can't be done. So the answers you got there with the yes, no's, those are the same ones I came up with. No for number 1, yes for number 2, yes for 3 and 4, no for 5, and yes for 6. So I guess we should start talking about, why is it that number 1 is a no and number 2 is a yes? I mean, the only difference between those 2 is just that extra little pit on the top. Looks like the roof of a house or the flap on an envelope. So I'll put those back up on the screen in just a bit, but I want to go over some terminology so that we're all speaking roughly the same language as far as some words. Let's start with vertex. Vertex is basically where two or more lines meet. And lines are actually called edges. They're not called lines. Okay, so an edge is a line, and then a vertex is where two or more edges meet. So if we go back to these pictures, here's a vertex, here's a vertex, here's one, there's one in the middle. And then for number 2, here's a vertex, here's one, here's one, here's one, there's one in the middle, and there's also one up at the top. So even though I could draw that figure without that vertex there, I could just draw kind of like a curved line. The fact that those two lines do meet at a point, that means that's a vertex. Number 3, vertex, vertex. Vertices all over the place. So the question is it the container the drawing is in? So is there something about, is there something about the outside outline? Like maybe this is the container for number 1, and this is the container for number 2, and this is the container for number 3. I guess the question would be for number 4 is what's the container? Like, how do we deal with this little thing? Is this the container? Is it like kind of like this? So let's try figuring this out. What is it about these drawings that makes some of them possible and some of them not possible? Let's just look at like number 1 and number 2 for now. Those are the simplest ones. Sorry, it's a little sloppy, but you get the idea. So for number 2, which we said is possible, you could start like here, and then go up and around, and then come back, and then zigzag through the middle. And then you can do it. Or you could start over here. Maybe you could go a different way. But it's still possible to do. Now, if I start, let's say, up in this corner, it's actually not drawable. Let me try doing it a different way. So if I start at that top left corner, I actually can't draw it. If I start in the lower left-hand corner, however, I can do it. So where you start actually has something to do with whether or not you can draw the picture. And here, excuse me, the answer is still yes, even though there are some ways in which we can't draw the picture. So the fact that there are some ways in which we can't draw the picture doesn't change the answer to the question. The answer is still yes, because there is some way to do it. Now for number 1, it doesn't matter where I begin. I always kind of get stuck. So it seems like the difference between number 1 and number 2 is this extra bit at the top. This somehow is instrumental in our ability to draw this one, and without that, it means that this one over here can't be drawn. So what does that change about the picture?
The vertex at the top of the box has one extra edge, both of them.
The vertex at the top of the box. Are you talking about this one here?
On the second one, the one like below the triangle, or just the box itself without. Yeah, the two vertex at the edge of them has one extra edge.
Oh, so the fact that we drew this little extra bit here means that this vertex now has an extra edge coming out of it, and this vertex now has an extra edge, and then somehow those two extra edges are the difference between this one is drawable and the other one is not. So there's something going on here, definitely. And that certainly is the difference between these two pictures. Everything else is the same. These vertices are the same, this one in the middle is the same. It's just these two at the top that are different. Someone here said evens and odds. Tell me about that.
So if a vertex has an even amount of edges, so if you start at going out, it's gonna go out in, and it goes in. You don't have another way out. But if it starts odd, it goes out in, out, and then if you can end with an odd, it goes in, out, in.
Okay, let's back up a little bit here. So first thing you're talking about is the evens and odds you're referring to is the number of edges coming out of a vertex. Is that right?
Yes.
Okay, so that, go back over to my terminology page. That's called the degree of a vertex. So the degree of a vertex is how many edges are coming out of it. So we can go through here and label these. This one is a 3, this one's a 3, this one's a 3, this one's a 3, and the one in the middle is a 4. And this one here is 3, 3, 4, 4, 4, and 2. So the degree does have something to do with it. In fact, it's almost the answer. And I think you kind of hit it on the head when we were talking about the odds and evens. But let's see if we can spell that out a little bit, step at a time. And so you said something about going in and out, in and out. So if I've got some vertex here, this is some random vertex, and I've got a degree of 4, which means there's 4 edges coming out of it, then I'm going to be drawing this picture, and at some point I'm going to come to that vertex. At some point I'm going to come into that vertex. And now I've got a choice. Which of those 3 edges should I take going out? Well, for the purposes of this discussion here, it doesn't matter which one I take. Let's say I take this top one here. I go out. And then I, draw the rest of the picture, and then I come back in to this one again. And now I've got only one choice. I have to take this last remaining one and go out. Okay, so if I come into a vertex of degree 4, I've got a choice of three edges to take. I choose one of them, and then now I've got 2 left. And so at some point I'm going to come back to this picture, or back to this vertex. I'm going to take another one of those edges, and then I'm going to use the very last one to go out. And so this is the case anytime the degree of the vertex is even. Every time you come to that vertex, you're going to use up 2 of the edges. One to go in and one to go out. So when the degree of the vertex is even, every time you come to that vertex, you use up 2 of the edges. But what if the degree of the vertex is odd? So you come into that vertex, you leave, and then you draw the rest of the diagram, and then you come back in, and now you're stuck. You can't go anywhere. So you can't leave that vertex. So that means one of two things. It means either you have to stop at that point, now you're stuck and you can't draw the rest of the picture, or it means something else. It means that has to be a vertex that you start or a vertex that you end on. Like, take a look at this drawing over here. All of these 4 vertices in the corner are of degree 3. So if I, let's say I pick this one down here in the lower left, if that's not my starting or my ending vertex, it means at some point I'm going to come into that vertex and then leave, and then I'm going to come in and I'm going to get stuck. Same thing happens over here. If I come into this vertex and then leave, at some point I'm going to come back to it and I'm going to get stuck. This one in the middle, number 4, I can come in and leave, and then I can come in and leave every time I use up two edges. So how about picture number 2? So here's a vertex with degree 4. Every time I come to it, I can use up a pair of edges. Even the one for number 2, or the vertex with degree 2, if I come to it, I can go out and use up both edges. But what about these 2 3s in the corner? What can we say about those? Oh, I think someone in the chat already hit it here. There has to be only 2 odds and the rest are evens, or it has to be all evens and no odds. So for the picture to be drawable, there has to be exactly 2 odds or none. So we'll say it has to be exactly 2 odds or no odds, 2 or 0. And you have to start on one of those odds and you have to end on the other one. So if I start here, I can draw this picture because I started here in the lower left and I end up on the lower right. Perfect. If I start here with number 4, I get stuck because I used up 2 of the edges going through this number 3, and then I have to come back to it, and I can't go anywhere once I come to it. So if I start on one of these 4s, it doesn't work. I have to start on the 3s. And if there's exactly 2 odds, then it's drawable. If there's more than 2 odds, in the case of this one over here, then it's not drawable because I'm going to get stuck somewhere. So let's see if that pans out for the other drawings. So first of all, let me start with something really simple. Like, what's the simplest picture that I can draw that is definitely drawable? And maybe that would be like a triangle. So it's got 3 vertices of degree 2. These are all evens, so it doesn't matter where I start, and then I can draw it. What if I make like an ice cream cone out of it? And I go 2, 3, 3. Is this one drawable? Well, I think it is. If I start here at this 3 and end at the other 3, I can do it. If I start at the 2, then it's not going to work. What if I have a triangle, but I add a little piece to it like this? So now I've got 2, 2, 3, and what about this last one over here? Is that a vertex? Well, it is, and its degree is 1. So I've got 2 vertices with an odd degree. I just have to start at one of those odds and end on the other one. So I can start here, and it's drawable. If I start at this one over here, number 1, it too is also drawable. If I start at the 2, however, I get stuck. So let's go back and look at these ones over here. So this one here, number 3, is drawable because I've got, I've got 3, 4, 4, 2, 3, 2, 4, and this one's also 4. So there's a 3 here and a 3 here, and those are the only 2 odds. So as long as I start or end at these 2 corners, I should be able to draw it. Number 4, I've got 2, 2, 3, 2, 4, and 1. So I'm going to start here and end here, or start here and end here. Number 5, I've got 3, 3, 3. Oh, already I can see I've got more than 2 odds, and so I'm pretty sure that cannot be drawn. And then number 6, I've got 3, 4, 4, 3, 4, 6, 4, 4, 4. So there's 2 3s. So that's a much better way to solve this problem, because I can now separate those 2 questions. I can separate the yes-no question from the how question. If I know the answer is no, I can't draw this, then I don't need to spend any time trying to figure out how to do it. If I know the answer is yes, then I can spend the time to try to figure out how to do it. And it turns out that the answering the yes-no question is really easy. All you have to do is basically count up the edges for every vertex and then just see if there's 2 or no odds. And if that's the case, then you know the drawing is traceable. If that's not the case, then you know the answer is not traceable. So I can look at an enormously complex picture and determine if the answer is yes or no pretty quickly. But the how question is a lot trickier. Think about how you would maybe program a computer to figure out how to do it. Now, once you knew where the odds were, that would make it a lot easier to know where to start and end. But you would still kind of have to use more or less trial and error to figure out how to actually draw the picture and not get stuck somewhere. Before we figured out this trick, before we figured out the degree of the vertex telling us whether or not the picture is traceable, we kind of had to use trial and error to figure out the yes-no question, and that's a terrible way to approach a problem. What you want to do is you want to try to figure out, is there a way for me to answer this question in a way that's not just what we call brute force, just trying every possible combination until we stumble across the answer. Like for number 5, it might take you a very long time using trial and error to figure out if the answer was no, because you're always in the back of your mind, you're thinking like, well, maybe I just haven't found the right path yet. I just need to keep trying more and more and more of them. And there's probably hundreds, if not thousands, of ways to draw number 5, to attempt to draw it. All these different paths you could take through there before you finally arrived at the answer of no, because you'd exhausted all the other possibilities. If the answer is yes, then all you have to do is find one way to do it, and then you know what the answer is. But it might take you a long time to find that one way because the picture is so complicated. Okay, so back to our terminology here. We've got vertex, we've got edge, we've got degree of a vertex. A graph is basically one of these things we've been talking about. A graph is a combination of vertices and edges. It's basically a picture, right? And then finally, an Euler path is what we've been doing. It's a way to trace the graph so that you cover all of the edges without skipping any or retracing any. And an Euler cycle is an Euler path that starts and ends at the same point. So over the next 16 weeks of this semester, we are going to be looking at a lot of different types of problems like this and being able to answer questions about it, like, is this possible to do or is this not possible to do? And if it is possible to do, how would you actually do it? And trying to separate those two things. One of the things that would be a very useful technique for any person, but particularly people who are into math and computer science, is to be able to prove something, to be able to form a logical sequence of steps that starts from a claim and goes to a proof. And these are really important to do in things like computer science because you want to know whether or not the program you're writing is correct or not. Like, I want to prove that my program produces the correct results. And one way to do a proof is what's called proof by exhaustion. You just try all possibilities. And in fact, that's usually the way we debug our programs, right? We write a program and then we just throw a whole bunch of inputs at it. And if it behaves correctly for all those inputs, then we say, ta-da, it's done. We've proven that it works. But that's not really a comprehensive proof because maybe there's some input that we missed that causes our program actually to not behave the way it's supposed to. And so it's useful to be able to start with a claim, a hypothesis, and go to a conclusion, and along the way make logical steps to be able to show that every single thing that I'm trying to claim is correct. Someone here says, one way to debug it is put print statements in your program, and if it prints out an error message, then you know it didn't work correctly, right? So here's my claim. So this claim, a graph cannot have one vertex with an odd degree, exactly one vertex. So the question there is, can I draw a graph that has a vertex with only one odd degree? Let me say that again. Can I draw a graph that has only one vertex in it that has an odd degree? All the rest are evens. And my claim is that you can't do that. You can't have a graph that has only one vertex with an odd degree. You must have at least two or none. And so one way to prove this is to assume that the opposite of my claim is true. Not that my claim is true, the opposite of my claim is true. So I'm going to assume that there is such a graph out there that has exactly one odd vertex. And then what I'm going to try to do is I'm going to attempt to draw that graph.
Yeah, are we supposed to share the notes?
Sorry about that. I sometimes forget to do that. I forget to, just remind me, if you can't see my screen, just shout out, I can't see the screen. Okay, so my claim is a graph cannot have one vertex with an odd degree, so I'm going to assume there exists a graph with exactly one odd vertex. I'm going to assume the opposite of what I'm trying to prove. And now I'm going to attempt to draw that graph. So one way to draw that graph is I'm going to start at that vertex. But I won't be able to complete the drawing because all the rest of the vertices are even. And as I go through all those even vertices, I'm going to be using up pairs of edges as I go, which means when I have used up all the vertices except for the last one, I'm going to have, I'm going to come into that vertex, and then there's going to be one edge left over. And I'll have to use that. So as we've shown before, if I start at an odd vertex, I have to end on an odd vertex. Sort of like almost by definition, right? I can't end on an even vertex because there will be one edge left over for me to use. So I can't end on an even vertex. I have to end on an odd one. But I said that there's only one odd. So this is a contradiction. But there's another way to draw the drawing, which is I could start at one of the even vertices. But that means at some point I'm going to encounter that odd vertex, and I will have to traverse it. I'll have to go through it. And when I traverse that vertex, I have to use up a pair of edges. And I don't have a pair, right? I don't have an even number of pairs. Or I should say I don't have a, yeah, you know what I mean? Like I don't have a set of pairs, right? We're going to have one left over. So this is also a contradiction. So both of these ways of attempting to draw the picture result in a contradiction. I can't assume that there's only one odd vertex and yet be able to draw the picture. So therefore, my assumption was not correct, and the opposite of not correct means the claim was correct. So this is one technique for proving things, is you assume the opposite of what you're trying to prove, show that this results in some kind of contradiction or inability to follow through with your logical reasoning, and then that means that your assumption was incorrect and that therefore your claim is Correct. Any questions before we move on? Had some people on YouTube also chime in. They are from Georgia, the country, and from Moldova. So we've got Vietnam, Serbia, Georgia, and Moldova, all over the world. Okay, so let's answer the question, what is discrete structures? What is this course about? I guess we should start by trying to tease apart what these individual words mean. Let's start with discrete. Okay, first of all, this is not the word discrete, which means like secret or private, right? It's not that word. So what does discrete mean? So we've got self-contained, not quite. So if something is discrete, what is it not? What is discrete the opposite of?
Continuous?
Oh, continuous, right. So it is not continuous. Maybe we could say they are separate or individual. So things that are not continuous could be things like integers. 1, 2, 3, 4, 5. So if we're counting along in these integers, we jump from 1 to the next. We go from 1 to 2, and then from 2 to 3, and 3 to 4, 4 to 5. Or we can even jump from 1 to 5. But what we don't do is we don't pass through all the values between 1 and 2 as we're jumping through the integers. So they're discrete because they go in steps. The graphs that we drew are also discrete because if I was to take this graph and I was to expand it, I would have to add a whole extra vertex or a whole extra edge. I can't add half an edge. I can't add a half a vertex. When I count the number of vertices in the graph, I'm going to end up with a whole number, not a fractional number. When I count the number of edges in the graph, likewise, I'm going to end up with a whole number, not a fractional number. So some things which are continuous, are things like the irrational numbers, right? All the real numbers, right? So basically, the numbers that contain everything between 1 and 2, all the infinite number of numbers in between there. But one thing which is not continuous, which is actually discrete, are floating point numbers, the kinds of numbers that your computer uses to calculate decimal amounts, like 1/2 or 3/5, right? So those are actually discrete because they go in steps. Believe it or not, there are actually in the range of floating point numbers, there are a fixed number of them, and they go in steps. There are some numbers that are right next to each other, and there's actually a gap in between those two numbers. And when you're counting using floating point numbers, you'll jump from this value to this value. You won't actually encounter the ones in between. So floating point numbers cannot represent an infinite number of numbers. There's a finite number of numbers, and therefore they're discrete. And they're actually going to be one of the first things that we explore probably next week as we go through this course. So let's talk about this word structures. This is a math term. It's a math term that means a collection of related things. So the integers is a structure. These are all related. They're like ways to count. Graphs are all related to each other because they're composed of vertices and edges. So that's what a structure is in mathematics. It's a collection of related items and the operations that act on them. Sorry, that's a little sloppy. Let me try to draw that again. Operations that act on them. So operations for things like integers is the mathematical operations like addition, subtraction, multiplication, division, plus all the other stuff you can do with them. Like you can compare two numbers. You can say this one is less than this one. You can take the set of integers and you can like expand them. I could take all the numbers, let's say from 1 to 10, and I could double them. So instead of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, it's 2, 4, 6, 8, 9, 2, 4, 6, 8, 10, 11, 12, up to 20, right? So I can operate on all those numbers and I could do something to them. So I like to think of this course as being the intersection between math over here and programming over here. And this section right over here, right in the middle, is where we are. So math, very abstract and theoretical. Programming, very concrete and practical. And then right there in the middle is where we are, where I'm going to show you the sort of the mathematical foundations behind all the stuff you're going to learn in your programming courses. So here are some of the topics we'll be going over. We're going to start out the next couple of weeks talking about data representation. Along the way, we'll learn how to count in binary, hexadecimal, base 10, other bases. We'll talk about ASCII and Unicode, so ways of representing text on your computer. Floating point number, fractions. Okay, so that'll be the first couple of weeks. And then we'll get into Boolean logic, and, or, not, exclusive or, and then followed very closely by gates and circuits. And so what this is Boolean logic are those operations like and, or, and not, and then the gates and circuits are the actual physical building blocks for a computer. All your computers, no matter how complicated they are or how sophisticated they are all built out of the same individual little components. And I'm going to see if I can find some of them. Do I have them sitting here? Nope. In my effort this semester or over the winter break to get organized, I put stuff away and then I promptly forgot where I put it. which is strange because I had props for like this course, stuff I'm going to use next week, and now I have to remember where I put it, right? Because I'm going to need it next week. Did I put it up there? Oh, I think it's up there. Hold on. I'm going to dive out of the picture for just a moment and go grab something here. See, now what I have to do is after I organize things, I have to label them so that when I look over there in my closet, I can see things. So like this was right here is digital logic circuits built out of parts that you can order from an electronic supplier. You know, in next week or so, I'll actually hook up the power and we'll see what this does. I'll be able to press these buttons and then this light and this buzzer will come on based upon what pattern of inputs I give to it. Here's another one. And so these are kind of like the basic building blocks for a computer. What this one does here, this adds 2 bits together. So I can put a bit A over here, a bit B over here. I can also put in a carry from another computation, and it will come up with the sum and the overflow. And so this is a 1-bit adder. It takes 2 bits, adds them together, and comes up with 1 sum. So this is, again, one of the fundamental building blocks of a computer. So we'll get to do some of that. You won't be able to build physical things like I will, but we'll build them in a simulator on the computer. So that leads into parts of a CPU. Did you see what I was holding up there? Hopefully, if you're watching this on Zoom, you've got things arranged on your screen so that you can see the screen that I'm sharing. In this case, it's my iPad that I'm writing on. You can also see me, so that if I hold something up in front of the camera, you can see it, so that I don't have to remember to do this. And so in case you missed it, this is what I was holding up on the camera. It's one of these. Okay, digital logic circuits, buttons for input, and then we've got here a light for sum and another light for carry. And then here's another one. Different circuits, same 3 buttons, and then a light and a buzzer. And then we're going to finish off the first half of the semester, the first 8 weeks, by talking extensively about cryptography, which I think is really important these days because you've got it involved in things like cryptocurrencies, Bitcoin and Ethereum, plus it's used to do things like protect your transactions on the internet, protects your banking, protects your shopping, even your instant messaging programs like WhatsApp and Instagram. Those all use cryptography to ensure that people can't snoop in on what you're doing. So in order to learn about cryptography, we'll have to study modular arithmetic, some basic ciphers like the shift cipher and the linear cipher, and then we'll talk about more complex ones like AES and DES, and then we'll finish up with RSA and ECC, which are 2 modern cryptographic systems that protect your transactions on the internet. And then finally we'll also talk about hashes, which are a way of ensuring that data that gets transferred from one place to another arrives intact without being corrupted. So that'll be the first half of the semester. And then in the second half of the semester we'll talk about sets, counting, which is another way of saying combinations, and permutations. Probability, but it won't be the kind of probability you study in a stats class. This will be called discrete probability, and it will have to do with events that either happen or don't happen, or maybe it's like a traffic light that has 3 discrete states it can be in, red, green, or yellow. Then we'll get into more about graphs. We touched on it a little bit today, but we'll do more with graphs, things like shortest path, how do you get from here to there in a graph? How do you use graphs to do things like resource allocation? And then we'll get into I need to spell here, regular expressions, finite state machines, which are things that look kind of like this. Maybe you've seen something that looks like that. Okay, and that'll be the second half of the semester. So we got a wide variety of topics to cover. This is kind of like a survey course of all these different topics that I think are important for a computer science student like yourself moving forward through not only this semester, but it branches out and connects with a bunch of different other courses. Like if you take a course in compiler design or programming language design, you're going to need those finite state machines, regular expressions, and graphs, and resource allocation. If you go in and take a course in, well, even if you're just doing your programming courses, you're going to want to know about like the Boolean logic and how binary, decimal, and hexadecimal work. If you are taking a course in, like your assembly language course, your computer architecture course, you're going to look at those gates of logic, and you're going to learn how to do minimization using like Carnot maps, and how to compose the different parts of the CPU using nothing more than these fundamental building blocks of ands and ors and nots. And of course, if you take a course in security, you'll do cryptography. So there's a whole bunch of topics here that are not just contained within this one course. They connect in with a lot of different other courses. And I really like teaching this course because it's sort of the aha moment for a lot of you. Like you've been studying these things, and you don't necessarily see the connection between your programming courses and some other course that you take, your compiler construction courses, and you want to go, what's the connection between those two things? And this course could help bring that out. I've heard from students who have gone on to transfer to other institutions to say that they really appreciated the fact that they covered a bunch of topics in this course because it gave them a little bit of a leg up on the students who hadn't taken this course before they transferred over to the other institution, and they got a little bit of background knowledge coming in where they were able to say, oh, I remember that stuff from the Discrete Structures course, and I'm able to now use that and leverage off of that to be able to be more successful in this other course. So as I discussed in my introductory videos on Canvas, there are a couple of prerequisites for this course. So one of them is Computer Science 12, which is our Intro to Programming 1 course. That's our first semester of programming courses. So this Discrete Structures course is one that you would take during your second or third semester. So either as a spring freshman or fall sophomore. The reason why we need that Computer Science 12 course is because it does lay the foundation for a lot of the stuff we're going to be talking about in this course, but also because we're going to be doing some programming in this course. And I want you to have already been exposed to things like variables, loops, conditionals, functions or methods, and so forth. We are going to be doing programming in a language called Python. Some of you have probably heard about this language. It is a fairly popular language these days for doing things like numerical analysis, scientific computations, and also even amongst computer people. There are a lot of universities that are not starting out with Java or C or C++ for their first introductory language. They're starting out with Python. And Python is said to be a lot easier to get into for beginners than a language like C or Java. I tend to agree with that, but that's not the reason why we're using Python. In this course, we're using Python as kind of a glorified calculator because it can handle things like big numbers without breaking a sweat. In a programming language like Java, once your numbers get above a certain value, like 2 billion or so, you get some weird effect, like either it might wrap around the negative numbers or it might overflow. But with Python, it just happily keeps computing, and you can end up with numbers that occupy pages and pages. And when we deal with our cryptography unit, we're going to have to be working with these really big numbers. So having a programming language that supports those big numbers is to our advantage. Python also supports the kinds of operations that we want to be able to do. As I said on one of the slides earlier, we're going to be studying sets, and Python supports sets. We're going to be dealing with recursive functions, and so Python, of course, can do that. Most programming languages can do that, but Python can as well. And also Python would just be a good language for you to have kind of in your toolbox when you're going forward in other courses. I'm not saying by the end of this semester you'll be an expert Python programmer. We're going to use a fairly limited subset of the language, again, kind of as a glorified calculator, but it does the kind of computations that we are interested in. A lot of the programs that we write in our Python are short, 2 or 3 lines of code, maybe 4 lines of code. It would take possibly several screenfuls or several pages of equivalent Java code to do those kinds of things, just simply because the Java language does not support natively the kinds of things that Python does. Now, there's nothing to install or maintain for you on your computers. Everything that you're going to be using in this course, it can be accessed from a web browser, even the programming environment. So I'm going to be providing that for you. We're going to get started with that next week, I think, as far as learning the Python programming language. And then the other prerequisite is Math 12, which is college algebra. For both of these courses, you don't have to have taken those courses at our institution. You could take equivalent courses at another institution and transfer them in. Why college algebra? Well, I guess the reason there is there's 2 algebra courses that we offer. There's college algebra and there's the, I don't remember what the other one was called, intermediate algebra, I think it is. And most computer science students who are going through our curriculum are going to take Math 12 because that's the one that's transferable to another institution. The other one, I think, is not transferable, at least for computer science. So most of you have already taken that course or are currently taking that course. So that shouldn't be a problem. And also, our transfer institutions expect that course to be in your transcript. Many of you have gone further. You're doing pre-calculus, you're doing calculus right now. And so you might even say, like, I took the equivalent of Math 12 back in high school. If that's the case, then talk to your counselor at our counseling center and have that credit transferred in. Okay, so those are the prerequisites for this course. And I should probably talk a little bit about our grading system. I am using a technique called ungrading. This is my second semester doing this for this course, actually just in general. The general idea behind ungrading is to remove the individual scores and grades that I would give for each separate little assignment. So you turn a homework in, I would grade you, 1 out of 10. I would, you turn in a program, I grade you out of 10. And I'll just say, over the past 10 years or so, I've found myself as a teacher increasingly dissatisfied with grading. Not only because I hate doing it, right? And the reason why I hate doing it is because I think it's just sort of inherently unfair to you and to me. Because what invariably happens is you turn in a program, and let's say it mostly works, right? It's got a few places where maybe it doesn't work, but overall it works, right? It comes up with the correct answer for correct input. Maybe it just doesn't handle incorrect input the correct way it should, but overall it works. And so, the question is, what score should you get? And so I hem and haw about that, and I go, well, it works most of the time. Maybe this student gets a 9.5, and then I have to write a justification for why I took off half a point. Or I say, like, well, it mostly worked, but the error that was made was, of a larger magnitude than this other student here. So I'll give this student, a 9 out of 10. And now I have to write a justification for why I gave that student 1 point off and the other one half point off for roughly the same error. Or maybe I just was in a bad mood that day, which happens sometimes, and I score people down, lower that day. And then there's other questions about, Well, let's say there's a student that comes into the course and they're able to consistently get B's, 80%, on all of their assignments throughout the entire semester. I mean, it's a fictitious student, but let's say this is happening. They get B's on every single assignment. And you've got some other student who comes in, starts out earning C's on their assignments, but through hard, diligent work is able to start bringing up their grade. They start earning B's toward the middle and start earning A's toward the end. Whereas the other student, the B student, just coasted all the way through, just earning B's. What grade should those students get at the end? And that was always a challenge, right? Most courses are graded using a system where you just average all the scores across the semester. And so the grade that both those students end up at the end is both a B, and yet the second student worked really hard and was able to bring their grade up. And the first student just coasted all the way through and kept the same grade. And so they end up both with a B at the end. And the third thing that I think is sort of unfair about grading is, what does that B or A or C actually represent? Does it mean that you did all the work, it was of perfect quality, but you were late on every assignment? Or does it mean that it was not of the perfect quality, but you were on time? Or does it mean that you worked really hard and you got that B because you didn't know any of the material coming in, or you coasted all the way through and got a B, right? None of that stuff is reflected in that grade. And so last semester I decided I'm just going to do away with all those little individual scores. We still have to give you a grade at the end of the semester. We still have to put something on the transcript. But I want to remove from you the stress of having to deal with those individual scores. And I want to remove from myself the stress of having to agonize over whether to give you a 9.5 or a 9 on an assignment. So that means that your individual assignments are just going to be given a complete or an incomplete. You've either completed that assignment to satisfaction or you haven't. And if you haven't done it, I will give you feedback. I'll say, here's where I think you could improve on that assignment. Turn it in again. And you just keep turning it in until either you decide you're going to stay with the incomplete or you're going to finish it until you get it complete. So what this means is that because I'm allowing you to turn in an assignment, basically as many times as necessary to earn that incomplete, there are no due dates in this course. I have put due dates on all the assignments, just as a way to keep you kind of on track, so that you know this is the assignment that is due on this date because we have just completed that, set of materials on these Zoom sessions and in the book. So I want those due dates to help you manage your time, but there is no penalty for turning an assignment in late. What's going to happen on your gradebook is as soon as that due date passes, if you haven't turned anything in, it's going to automatically score you an incomplete, and you'll get a little notification that you haven't completed that assignment. That, I hope, will help you keep up with the assignments, but remember, there's no penalty for then going back and turning in that assignment. Just because an incomplete appears in your gradebook doesn't mean it's done. It means that you can still turn it in. So another follow-on to that is, if you find yourself overloaded with work, let's say you've got your physics class or your math class, and there's a test coming up, and you really just need to spend time studying for that class or completing that assignment, and you don't have time to do my class, that's fine. Put it off for a day or two. Get the assignment in a little bit later. I'd rather you turn it in late than stress about trying to turn it in on time and not meet your other obligations. Okay, so that all being said, one of the things I discovered last semester was it was very easy to procrastinate and put things off. I had a lot of students that turned in all their stuff during the last 2 weeks of the semester. And that's not fair to me, because now I have to grade all that. I'm not going to use the word grade. I have to evaluate all of that stuff in a very short amount of time, and I can't give you the kind of feedback that I want to be able to give you so that you can bring your quality up. So keep that in mind. If you procrastinate, you're affecting not only you, you're affecting me as well. You can procrastinate by a little bit, turn in something a week late, a couple days late, but please don't wait till the end of the semester and try to cram it all in. Halfway through the semester, we'll have a check-in. I'll have you fill out a little self-evaluation about how you're doing in the course. We'll look at it, you and I, and then we'll just kind of use it as a way to remind you that you need to keep up with the work in the course. So we'll talk more about the ungrading as we go through the semester, but there is a discussion on Canvas already for you to participate in and tell me what you think about this policy. What has been your experience in the past with traditional grading, and then what do you think is going to be the pros and cons of doing this ungrading system in this course? If you're taking my other course, my C programming course, you'll find that I'm doing the same thing over there. Let's see, let me catch up on some of the chats here. So we have some people from India and Northern Virginia. Welcome. And also, we have someone who said, Sac State does require Calc 1 to take the Computer Science 26 equivalent there. So you're right. Sac State does require Calculus 1. What we did is I talked to the instructor over there, or at least the instructor who was teaching this course, the equivalent course over there at the time. And he said, yeah, Calculus 1 is a prerequisite for our discrete structures, but there's two reasons for that. One is almost all of our students have taken Calculus 1 anyway, coming into Sac State, and so there's no problem making that a prerequisite. And I guess that was the primary one. And then we looked at what was actually required to be successful in discrete structures, and it turned out there was little or nothing in Calculus 1 that discrete structures actually needed. Everything that discrete structures needed was in algebra. And so when I designed the curriculum for discrete structures for Sierra College, that was one of the things I did, is I said only college algebra is needed, because I was able to actually list out, here are the skills from college algebra that you need to be successful in discrete structures. There was nothing in Calculus 1 that was, inherently useful, or more useful than college algebra was. So when you transfer over to Sac State, you will still need to take Calculus 1, but by taking discrete structures here at Sierra College, you only need college algebra to be able to take it. So you can take this course earlier in your college curriculum than you can over at Sac State. Okay, so I think that is pretty much all the stuff I had for you today. It is approaching, 10:45, 10:47, so we're nearing the end of what would usually be our lecture time. Are there any questions from you before we end this?
When it comes to doing discussions, is it okay to do a video response rather than a typed one?
Of course.
All right.
Yeah, that'd be cool. Anybody else?
What can we expect during our lab sessions? Like, what exactly are we going to be doing?
So nearly every week, especially during the first half of the semester, there will be weekly programming or assignments you need to do. And so those lab times will be a time for me to introduce the material, and oftentimes I will basically walk you through the lab assignment, the programming assignment. I'll leave little gaps in there. It says, I'll show you how to do box number 1, but you have to do box number 2. Does that make sense?
Yeah, thank you.
Yeah, so I will introduce the programming assignment, and I will also, in many cases, walk you through how to do that assignment, leaving you to fill in the gaps, but explaining what each one of the questions are. Because I understand a lot of you don't know Python. This is your first time doing it, and so I'm going to hopefully be able to answer your questions during those times about how do we do this, how do we do that. The question was, with ungrading, does the end grade give you a pass-fail grade instead of a grade? an A to F grade? No, at the end we'll give you an A to F grade. So what will happen there is over the semester, you're going to accumulate essentially a portfolio of completed assignments. You've got your programming assignments, you've got homeworks, quizzes, discussions, all that stuff goes into the, I'll call it a portfolio of stuff that you did during the semester. And then at the very end, I will ask you on a survey that you'll fill out, what grade do you think you should get in this course? And you'll look at what you've done, and you'll say, I think I should earn, let's say, a B, and I'll ask you to justify why you think you should get that grade. And then we will meet during the last week of the semester for about 5 minutes on Zoom, and we'll talk about that evaluation that you gave me. And we'll arrive at a consensus about what grade I'm actually going to submit for your transcript. So it won't be me just handing down and say, you're going to get a B. It'll be you and I collaborating together to arrive at what grade you're going to get. I hope you'll find this to be a very rewarding experience because you have a say in what score you get or what grade you get. It's not just me, sitting on a cloud somewhere, just throwing grades down at the students who are sitting on the earth trying to collect them, right? So this is one of the things to bring up in the discussion is what are some of the concerns you have about the ungrading system, and then hopefully we can answer some of those. Oh yeah, so it's kind of like you agree on a grade, kind of like in a job offer, right? So the employer makes an offer about how much you're going to earn, you counter with your offer, and then you meet somewhere in the middle. Any other questions? Someone on YouTube asked, I arrived extremely late. Will you post a synopsis of the most important issues that will be helpful going forward? Well, all the recordings, of course, will still be there after the live session. So you can go back and rewatch the whole video from the beginning. So will that be helpful in obtaining the things that you need? Now, YouTube is on about a 20 or 30 second delay. So I answer the question for the YouTube people, and then they get it in 20 seconds, and then they respond. So for the Zoom people, there's only about like a half-second delay. So, you and I can actually have a conversation, but the YouTube people have to have that delay. So if you weren't here at the beginning, I am dual streaming this to Zoom and YouTube. So those of you who are in my course, you're watching on Zoom. You don't have to show yourself on camera, but it would be nice, to see you once in a while. And also, the people who are on YouTube get a slightly different stream. They get the same thing that you're seeing right now, but they can't see your faces. So they can only see my face on there. If there's anything that happens that's private or has to do with only the course itself, then I will mute the YouTube stream. It will cut out the audio and the video, and only the Zoom people will be able to hear and see what's going on. So if you have to ask questions about, school policies, or you have, a complaint about something, I will mute the YouTube stream, and the Zoom people will only be able to hear what's going on. Is this a free course? I guess so. You're getting it for free. And it's live. So there's almost nothing here that's pre-recorded. I might occasionally show you a video, right? But it's all live, and it's all based upon what you are putting into it. So if you have a question for me, and it's related to what we're talking about, then I'll try to answer it. So what's going to happen now when it comes to 11 o'clock is I will end the Zoom session, also end the YouTube stream, and then I will switch over to the student hours. So we call it student hours, other institutions call it office hours, but it's a time where you'll be able to come onto Zoom and just have a one-on-one with me. If you have questions about the course, you need to add the course or something like that, then come into that and I will gladly take care of those things. Oh, by the way, those of you who are trying to add the course, actually, I don't think anyone's trying to add this course. This is like the first time in I don't know how many years when this course is actually not filled up. We got a few slots available. So If you need an ad code for this and you somehow stumbled across this video, then just shoot me a message and I will give you one. Okay, well, I think that's it for now. We're going to end this. We're going to say goodbye for now. We'll be back on Wednesday, same time, 9:30 in the morning until 11 o'clock. And then we'll take a short break and then we'll go. Actually, this week we don't have a lab session. So we'll be ending at 11 o'clock. Following week, Monday, we will have our usual lab time, lecture time from 9:30 to 11. And then on Wednesday, it'll be 9:30 to 12 o'clock because it will include that first lab time. We'll get a little break at 11 o'clock. Okay, I think that's it. Have a good day, everyone.
See ya.
Bye-bye.
Thank
Have a
you.
good one.
Take care, everyone. All right, those of you who are on YouTube, you're just going to watch on YouTube. If you're not a Sierra College student, then you just watch on YouTube. If you are a Sierra College student and you want to add my course, then send me an email and I will get one of those ad codes to you. You have to tell me which section also you want to add in. I have 3 sections running simultaneously, so you'll have to give me the course code, which is the 5-digit code, and then I will give you the ad code, which is the 4-digit code. 4 digits, or is it 6 now? I think it's 6 now. Okay, so that's it for the YouTube stream. I will see you back here on Wednesday, 9:30, at least my time. I don't know what time it is for you. I imagine for some of you it's actually in the middle of the night, so I really appreciate that you're able to stay up and watch this. Do I have programming courses on Tuesday and Thursday? Yes. I have my System Programming in C course on Tuesday and Thursday. Same time, 9:30. You can actually catch a lot of the sessions I did last semester, back in, what was it, September through December, on my YouTube channel. So this is kind of like just going full circle again. I started doing the YouTube streaming halfway through the semester, and so now I'm going to do the other half, but I'll just keep going all the way through. So you'll get like a complete C programming course over the next 16 weeks on YouTube. All right. Well, have a good day, everyone. I will see you certainly by Wednesday, but if not, I'll see you on Tuesday, tomorrow, for my other course. Take care. Be safe. Be good to yourself and others. Bye-bye.